Hello, I'm Shujat Khan, and here I will present to you my recent work on deep learning based beamformer for variable rate ultrasound imaging. My co-authors are JM and Professor Jomchulye. I'm a PhD student at Department of Bio and Brain Engineering, KAIST. So let's get started. As we know that the ultrasound is a safe modality, so why it is safe? Because it's a non-invasive, radiation-free, and real-time acquisition imaging modality. That's why it is considered as a first choice for a variety of clinical applications such as fetal or cardiac imaging. Before presenting my actual work, I would like to give you a brief introduction on ultrasound imaging mechanism. Basic imaging principle of ultrasound imaging is based on time reversal, which is based on mathematical observation that the wave operator is self-adjoint. In other words, the wave operator is invariant under time transformation and the position of sources and receivers can be swapped. For example, as shown in figure 1, the return echoes from individual scan lines, especially in focused beam mode imaging, are recorded by multiple receivers. Since receive measurements from multiple channels are not in phase, therefore, uh, delay in some beamformer applies time delay to the receive measurements and combine them to form image at each scan line. Here, the in delay in sum, usually a simple addition operation is performed for beamforming. However, for adaptive beamforming or advanced beamforming techniques, there are varieties of ways which you can use for such as weighted sum and etc. This is called apodization. Yeah, this is sum. So in conventional beamforming pipeline or conventional delay in sum beamforming pipeline, uh, focus signals are additively combined, followed by Hilbert transformation, envelope detection, and log compression steps. Despite the simplicity, large number of receiver elements are often necessary for desired quality image, which can be used for clinical purposes. However, in portable three-dimensional and ultra-fast ultrasound imaging system, there is an increasing demand for the reconstruction of high-quality images from a limited number of radio frequency measurements. To solve this problem, I designed a beamforming framework for undersampled data. In proposed beamforming pipeline, the simple adder and Hilbert transformation blocks are replaced by a deep convolutional neural network. More detail on the proposed pipeline in the later sections. In adaptive beamforming, the objective is to find the weights that minimize the variance of the RF sum, which is now a weighted sum, as shown here. The, the weight that we find to minimize the variance in the RF sum are bounded by the constraint that the gain in desired beam direction should be equals to unity, should not be more than unity. For minimum variance estimation, a covariance matrix must be estimated with a limited amount of data. A widely used method for the estimation of covariance matrix is spatial smoothing, which is also known as subaperture averaging. One of the main limitations of the conventional beamforming method is that they are based on rare approximation of the wave propagation, whereas real sound propagation exhibits many wave phenomena such as scattering, etc. Moreover, the precision of the time delay calculation is determined by the bandwidth of the transducer, which limits the accuracy of the delayed signal. These modeling inaccuracy indeed affect the spatial resolution and the contrast of ultrasound images. In order to overcome these issues, the deconvolutional ultrasound tries to find deconvoluted signals, just shown below as here highlighted one, where I is an identity matrix of size L by L. L is the active aperture size, which means like how many receivers you are using to scan a scan line. Y denotes the RF vector, which is also equals to the length of n, uh, which is acquired for the depth n. Let's say you have uh, lots of depth sample, because because each scan line is composed of a time series which has certain length, and each time point in that time series can be represented by the index n. So y denotes a vector of a RF signal that we acquired at depth n. V is the IQ channel data. Here IQ represents the in-phase and quadrature signal, which we obtain after n-load detection step, which is usually performed by Hilbert transformation. W and H are the beamformer weights and deconvolution filter matrices respectively. Accordingly, above equation can be simplified as follows, where B and B tilde denotes the deconvolution filter matrices, and U represents the input RF vector across multiple depths. So U is nothing but just a matrix representation of Y for multiple depths. According to the deconvolution model, the RF image obtained from the raw data after beamforming operation can be represented as a convolution between point spread function and the tissue reflectivity function. So we divided the signal, the beamforming operation, into two steps. One is related to the system itself, which is defined as a point spreading function, and one which is only related to the object that we are scanning. So it's a tissue reflectivity function. The tissue reflectivity function can thus be recovered from the RF image using deconvolution algorithm. And the quality of RF image, which has an impact on the recovered tissue reflectivity function, is linked to the beamforming technique. Now, the aim of ultrasound reconstruction is then to find the deconvolution filter matrices so that the process image has high resolution with good quality of in terms of the contrast, or in the other words, the signal to noise ratio. In practice, the estimation of tau in equation 9 is technically challenging, and therefore we need to find some way so that we can solve this. In addition to this, the deconvolution filter matrices B and B tilde should be spatially varying and depend on input signals to make the best trade-off between the noise and resolution. Therefore, the exact calculation is usually computationally expensive and only approximate forms are used, which limit the accuracy of the beamformer. A quick remedy to reduce this runtime computational complexity would be pre-calculating the nonlinearity in tau. Unfortunately, as stated before, the mapping depends on the input signal, so it requires huge memory to store tau for all input patterns, or at least all most of the input pattern, because the number of it's a combinatorial problem, and there are uh, tons of possibility your signal can vary in various ways. So storing this nonlinear mapping is very it's actually a very huge combinatorial problem, and it's almost practically infeasible to store all possible patterns. In this regard, a convolution neural network with a ReLU nonlinearity provide an ingenious way of addressing this issue. Especially in a recent theoretical work, we have shown that an encoder-decoder neural network, convolution neural network with the ReLU nonlinearities, generate large number of locally linear mappings. More specifically, the input space is partitioned into non-overlapping regions where input for each region share common linear representation. Then switching to the corresponding linear representation for each input can be done instantaneously based on ReLU activation patterns. So for combinatorial representation learning, we can use CNN, and by following the derivation from the referred paper, it is straightforward to show that the output of encoder-decoder CNN with respect to RF data can be represented by a nonlinear frame-like representation as shown below. Note that the CNN-based representation is strikingly similar to our adaptive beamformer representation in 9. This implies that the adaptive beamforming can be learned using encoder-decoder CNN. For example, the neural network can be trained to estimate the convolution filter matrix or convolution filter, which has coefficients theta, can be represented as follows, where Z and VA denotes the training dataset composed of RF data uh, at a particular depth, and VA is a IQ data at the same depth, which are collected across multiple depths, subjects, and subsampling patterns. Before designing a CNN for subsample data, we need to know the nature of the data, whether the data has any sparsity in it, or is it possible to perform compressive sensing or subsampling in the data or not. So as we know, in focus beam mode imaging, the direction of each transmit event changes incrementally. So the acquired data does not change rapidly. This implies that some degree of skew redundancy exists in the receiver scanline coordinate, and can be easily seen as a sparsity in the Fourier domain as demonstrated in figure 3. This skewness can be removed by applying the delay and by just focusing the signal. So there exists some redundancy that we know in the scanline and the receiver coordinates. Similarly, there is high correlation in the data across the depth as well, because the neighboring planes are acquired with high sampling frequency. In the depth plane, we have high sampling frequency, so neighboring or adjacent planes are very much similar, or may have some uh, redundancy in them. So I call this redundancy a temporal redundancy, and the previously mentioned redundancy as a spatial redundancy. So therefore, to exploit this spatio-temporal redundancy, I use multi-line multi-depth approach. The proposed CNN model is a multi-channel unit-like encoder-decoder neural network with skip connections, and obviously the ReLU non-linearities. I call my proposed CNN model a deep BF, which is a deep neural network based beamformer. It can directly process subsample RF data to generate high quality IQ data. Here, RF data obviously is not just directly measured, it is after focus. So the only difference is we apply time delay to the measurement, and then we give it to the CNN. Extensive experimental results on in vivo data as well as on phantom data with various subsampling schemes confirm that the proposed DBF model can effectively reduce the data rate without sacrificing the image quality. So let's just see the results. Interestingly, for fully sampled in vivo data, the proposed DBF method outperformed the conventional DES and MVBF method. Here I would like to point out that the proposed DBF was trained to mimic IQ data of fully sampled DES. However, it learned to produce images even better than MVBF. As you can see in the anechoic region, there is less noise in DBF images compared to DES and MVBF. Another issue that usually faced by the adaptive beamformer or neural network based beamformer is that the signal on the near field and far field show different behavior, and that's why we need different apodization weights for different depths. But in our case, the proposed DBF successfully reconstruct both the near and far field region with equal efficacy. That's amazing. Furthermore, the contrasted DBF is comparable or even better than MVBF. For example, GCNR value improved from 0.94 to 0.95 in example 1, and the similar improvement can be seen in example number 2. Here, GCNR is a measure of contrast between two regions, and it is defined as 1 minus overlap in the pixel intensity distribution of two regions. This performance measure is much robust, like much more robust than the CR and CNR, which is just a contrast ratio and contrast to noise ratio. And GCNR is a generalized version of CNR. Because CR and CNR, especially CR, is highly sensitive to the dynamic range selection, and CNR also it does not have any defined scale, but the GCNR is defined a scale of 0 to 1, where 0 means no contrast at all, and 1 means you can distinguish two regions with 100% accuracy. So that's why the GCNR is actually considered as a much better performance measure. So that's why we emphasize, and maybe in the later slide I will use GCNR as a map performance measure. In addition to fully sampled data, the proposed DBF can also generate high quality images even with subsampling subsample measurements, which I mentioned before. So let's just see the subsample results. Here I show you image reconstruction results on in vivo data for variable subsampling schemes. From reconstruction results, it can be easily seen that for all downsampling schemes, the proposed method outperformed the conventional beamforming methods. This improvement in subsample data is prominent in difference images. The difference of fully sample and subsample reconstruction is shown in normalized scale. In the these blue images are difference images. Especially at high sampling rates, there is a graceful degradation of visual quality in DBF compared to DES and MVBF, which show drastic reduction in the quality at a higher subsampling rate. Especially at high sampling rates, uh, there is a graceful degradation of visual quality in DBF compared to DES and MVBF. Uh, yeah, this could be easily seen in the difference images as well as in the zoom region. For quantitative evaluation, we compare PSNR, SSIM, CR, and GCNR distribution of DES, MVBF, and DBF for 360 in vivo scans on variable subsampling rates. As shown in table, the GCNR value of DBF does not decrease even for 2.7 times subsampling, and only drop by 0.01 units for 4 times downsampling. It is noteworthy to point out that the CNN-based model is used to generate images for a single, actually it's just a single CNN based model is used for all subsampling rates. So we didn't train separate model for separate sampling factors. We just use one model for all subsampling factors. So these results show that our CNN model is very generalizable, and it's the results are very amazing. So to test whether this improvement is real and not the artifact, we test our model on phantom dataset as well. Again, in fully sampled phantom case, the DBF achieve comparable or even better performance than MVBF. For example, in terms of CR, there is consistent performance improvement in DBF. Similarly, in GCNR, we also outperform the conventional beamforming method, for example, from 0.81 to 0.82 in example number 2. We also tested the same model for compressive beamforming case. Here, I show an example result from an echoic phantom. The reconstruction results using DES, MVBF, and DBF are compared for variable subsampling rates. In difference images, it is quite prominent that the conventional beamforming methods fail to maintain the quality at high sampling rates, whereas the proposed DBF show graceful degradation of visual quality. Here, for quantitative comparison, we acquired 218 phantom scans from the tissue mimicking phantom and calculated a distribution of standard performance measures, which I mentioned before. The distribution curve clearly depicts the performance gain achieved by the DBF. Interestingly, this time the DBF show even better performance than the in vivo scenario, and the average GCNR value remained constant even at 4 times downsampling. A relatively similar behavior is shown in other performance measures as well, like PSNR, SSIM, and CR. You can see that the performance does not decrease rapidly, it just linearly goes down. Uh, but after 4 times downsampling, it suddenly drops. So yeah, 4 times is actually a huge number if you compare subsampling factor. Finally, in figure 10, we compare lateral and axial profiles through the center of phantom and a coexist using DES and proposed DBF method. From the figure, it can be seen that under all sampling schemes, on the boundary of the cyst, the proposed method shows sharp changes in the pixel intensity with respect to the lateral position in image. So, in terms of the lateral profile, we can see there is a prominent uh, difference in DBF and the DES beamformer result. Although the axial profiles show similar trend to DES, so no, but but the uh, but there is no significant degradation in the axial resolution in subsample images. Like if you see 16 times subsample result and fully sample case, there is no significant degradation in the axial resolution. This is because we have high sampling frequency in axial dimension. Like if you see the lateral dimension, we have 192 channels, and at maximum here we use 96 scan line. So we just have 96 scan line in lateral dimension. So subsampling degrade the quality significantly. Whereas in axial dimension, we have very high sampling frequency. That's why just reducing even at 16 times downsampling, there is no significant degradation in the quality. And I think if we use more depth planes, because in our DBF we just use 3 depth planes, you can increase it to 5, 10, or even 11, or whatever number that you prefer, depending on the quality improvement you want. But obviously there is a trade-off between the complexity and the quality. But here I show the purpose of showing this is that because there is no significant degradation, so there is no improvement either. The conclusion of this study is as follows. A single universal deep learning based beamformer can generate high quality beam mode images. The proposed method is purely a data driven method which exploits the spatiotemporal redundancy in the raw RF data, which help in generating improved quality beam mode images using fewer receiver measurements. The proposed method improves the contrast of the beam mode images by preserving the dynamic range and the structural detail of the RF signal in both the phantom and in vivo scans. Due to the exponentially large expressiveness of the deep neural network, the proposed DBF can effectively learn various mapping from the RF measurement and exhibit superior image quality for all sampling rates. And we actually try to give a theoretical justification for this improvement, which is linked to the deconvolution ultrasound theory. Therefore, this method can be an important platform for RF subsample ultrasound imaging. That's all for my presentation. Thank you for your attention.